So hello everyone, and welcome to MacDermid Enthone's discussion today on the aluminum service technology requirements for electric mobility and anodizing. My name is Robert Collin. I am the Americas Technical Manager, and I'll be the moderator for this event today. The presenter is Sasha Wegner. He is our anodizing product line manager from MacDermid Enthone for the Americas. Any and all questions you have, please submit them in the questions side of the chat on the webinar. We'll answer as many of these questions as we can at the conclusion. If we do not get to your question specifically, we will email you and have a discussion from there. Again, thank you all for taking the time to learn about MacDermid Enthone's anodizing portfolio to meet the needs for electric mobility and beyond. And Sasha, the session is all yours.
Thank you very much, Rob, and good morning or good afternoon to everyone, depending on where they are in the country. My name is Sasha Wegner. I'm the product line manager for anodizing products in the Americas. And I have been with the company for quite some time. I think it's been over 20 years, and I have worked in many different fields and positions, and actually in all across the world, in Europe, Asia, and just recently for the last 2 years in the Americas, where I've taken over the product line for anodizing products. So without further ado, what I want to go into today is, I just need to move on the first slide. The agenda. Let me go quickly into the agenda for today. So this is all about requirements for the aluminum surface technologies with a view to the light vehicles and electromobility EV vehicles. We will look a little bit at different technologies to treat these aluminum surfaces, and these are going to be conversion coatings and also anodizing finishes. Of those finishes, we'll have a look into some applications, and again, these are going to be battery housings for the conversion coatings, and for the anodized finishes, we will have a look into brake components, and then also at some exterior trim and roof rail applications. The importance for aluminum and these lightweight materials in the automotive industry really stems from the reduction in vehicle weight, and that is something that directly translates into fuel efficiency and reduction in energy consumption for EV cars. And that obviously in turn means that we extend the range of these vehicles significantly. Also, the use of aluminum in cars these days has a lot to do with recyclability of vehicles. And there's a statistic that about 80 to 90% of all aluminum in circulation at the moment was actually produced and manufactured from recycled aluminum. If we look at the lightweight materials by industry here on slide number 4, we have broken that down into the 3 main industries. One is the aviation, one is the wind turbine industry, and then the automotive industry. And what we can see over the span of 20 years from 2010 to a projected 2030 here, we see a very stark increase in the use of lightweight materials. And these lightweight materials are aluminum, obviously magnesium, plastics, carbon fiber, and also high strength tensile steel. If we look here on the right, we can actually break that down by unit for this industry. So in the aviation industry, we're obviously talking about planes, and we can see that as of today, or 2010, there was about 78% of planes made up from lightweight materials. That will still increase by 2030 to 85%, or an increase of around about 7%. For the wind industry, we're a little bit stagnated here. We don't really see an increase at all in lightweight materials here, but very significant growth in the automotive industry, and where we used to see around about 29% of cars made up from lightweight materials, by 2030 that will increase to around about 67%, or an increase of around about 38%. If we move on to the next slide, we can actually break that down by the base materials or by the lightweight materials. And what we see over the years and the forecast is a reduction in steel. And obviously that steel will be replaced by lightweight materials. We can see that here, the high strength steel fasteners, a lot of fasteners, these can be produced in smaller dimensions, and through those smaller dimensions, we can decrease the weight of those components. Carbon fiber sees a big increase in percentage, but when we look at the volumes, they're actually pretty insignificant, and that really comes from the cost of carbon fibers and the type of vehicles they will be built onto. The main interest for us really here and for our industry are the aluminum components. And again, what we see over the next few years and decade is a very significant increase of the use of aluminum in the automotive industry. So if we move on, we see an exploded picture here of a car, and that really shows that the differences between the combustion engine cars as we know them today and the future EV cars. And when we break it down into components here, there is not really a big difference between the traditional cars, combustion engines, and the electric vehicles, except for the engine block that will obviously be replaced by electric engine, and the EV cars will also include a battery construction or a battery housing, whatever definition and terminology we would like to use for that. The aluminum alloys that are predominantly used in the automotive industry are listed here. So we have the 5000 series aluminum alloys that are alloyed with magnesium. They're really used for panels, used for some bright trim work for exterior trims. Then we have the 6000 series, the traditional extruded aluminum alloys using magnesium and silicon as alloying material. And then we have the high strength alloys, 2000 series and 7000 series. These contain a lot of copper, and in the case of the 7000 series also some zinc. And then various cast aluminum alloys here, mainly used for battery housings, for brake components, so on and so forth. So what I want to do is I want to go into some of the surface treatments we offer here. And the first one I would like to talk about is the aluminum conversion coatings. And the product range we offer for these coatings are our erudite products. And when we look at the requirements for conversion coatings, it's very clear. They are applied to offer corrosion resistance. Whether this is as a final finish without any further treatments, or whether they are used as a pre-paint finish for pre-paint application. And in those cases, they obviously have to still offer the good corrosion resistance, but in addition to that, they will also have to offer paint adhesion or certain other requirements like bonding properties to rubber bonding applications, so on and so forth. In some cases, and again for the battery casing that is important, they have to offer electrical conductivity. So they can't be too thick. They still need to be able to have a low resistivity so that in cases of any short circuits, the battery casing can be grounded and doesn't offer any hazard. So moving on to slide 10 here, I have tried to break down the different technologies for conversion coatings here. And there are probably many more out there. Well, I'm trying to group them a little bit here for easy understanding. When we look at from the left here, the erudite NCP, these are chrome-free products based on zirconium inorganic compounds. They are mainly used as immersion and spray processes, and they're really designed for general use as a final finish to offer good corrosion resistance. They're a little bit limited to their use when it comes to the alloys, and that's one of the reasons why we have developed other passivates. And these are in the middle here, the erudite TCP3. They're not just zirconium-based products, they also contain a portion of trivalent chrome. They work very much in the same ways as the zirconium-based processes, again as immersion and spray processes. But what they do is they offer very good corrosion resistance for higher alloyed aluminum substrates, and in particular when it comes to copper and zinc alloys, these will perform much better. The third group here are the erudite NR2I and NR24T. These are products, again, chrome-free based on zirconium, but these compounds are actually built into a organic polymer matrix. And the difference here, they're also immersion and spray processes, but the difference here is they don't actually need a final rinse. These processes get baked onto the surface, and this is the final step prior to any paint application that is required. So again, the application here is pre-paint and not really as a final finish like the erudite TCP3 and the erudite NCP. If we look at the chart here, this is really a comparison between the chrome-free products and the traditional hexavalent based products. And when we look at the comparison here, the bar charts, we see that the chrome-free products perform extremely well in a very similar way to the hexavalent chrome products on aluminum alloys such as 5000, 6000, 1000, and 3000 series. In some cases, they even outperform the hexavalent chrome products here. But when it comes to the copper alloyed aluminum alloys here, we see they struggle. And especially when we look to the right of this chart here, we see the 7000 and the 2000 series here. And that's where these chrome-free products struggle a little bit, offering good corrosion resistance. If we move on and we see the table here for the Iridite TCP3. If you remember, this product contains an amount of trivalent chrome, and when we go down the left-hand side here by the type of alloy, we can see that for the 2000 and 7000 series alloys, we can achieve much higher corrosion resistance compared to the chrome-free product. We're in excess of 200 hours, 300 hours for some of the 7000 series products here, meeting all the relevant specifications. One of the applications for these conversion coatings, which is relevant to us, are the aluminum battery constructions. And this is really the battery surround technology. And if we move on here to slide 14, we can see why it's so important to protect the battery housings. These are installed very near to the ground of the car, and that is really done for one reason, and that is to lower the center of gravity and to improve the handling of the car. It's very different to the old hybrid cars, which had much smaller battery packs, and in those cases it was able to actually put them in the trunk or make them part of the trunk and have them slightly higher in the car. But now, because these battery cases for the EV cars are so close to the ground, they're actually very much exposed to the environment, to any sort of damage from the roads, so on and so forth. So the concern really here is that because of these of the impact from the road, that there is the possibility of the environmental, any liquids, solids, to intrude into the battery construction, and obviously impair the functionality of this battery construction. If we look at the battery enclosure, the requirements, it's quite clear, and this is what we just discussed. We have to make sure that there's no ingress of any fluids, of anything from the exterior environment into these battery cases that might impair the functionality of the batteries and the electrical circuit. Part of that is obviously to offer very good corrosion protection, and make sure that the sealing surfaces between the lid and the housing itself doesn't get compromised. We need good grounding ability, so for any short circuit, or in an event of a short circuit, that we actually trip the switches or blow fuses to make these assemblies safe. And then for any paint applications, if these battery cases receive paint or e-coat, we have to make sure that there's a good adhesion between these battery housings and the final finish, the paints. When we look at the design of these battery constructions, in a lot of the cases we deal with cast aluminum trays or housings here with high silicon content, because it is a cast component. We have relatively high copper concentrations as well, which makes it sometimes necessary to use trivalent passivates. We have other cast qualities here, like the A304, or in some cases, these trays or boxes are actually deep drawn from extruded 6000 material. For the lids and the covers, the range of materials varies even more, from cast aluminum over stainless steel or galvanized and e-coated steel lids to polymers or plastic lids. This great range and this very new application really for battery housings has actually shown that most OEM specifications are not really designed, and they don't cover the aluminum battery requirements at all. Because of the contact corrosions and the different materials that are part of this assembly, OEMs are still trying to develop specifications, and they're going through a lot of different testing of various systems to finally agree what they will specify and how they will write the specifications around these requirements. One of these specifications here really asks for corrosion resistance, and what some of the OEMs have done is they have miniature assemblies where they use two different substrates. These are separated through a O-ring, a rubber gasket, and then those assemblies are submitted or exposed to cyclic corrosion testing or salt sprayer testing. And what they're checking for is really the undercutting of the sealing surface here. And the specification currently really calls for less than a 50% undercutting of the sealed surfaces, which would be a pass for some of these OEMs. And we can see that here quite nicely after disassembling these parts in the red area here. This is completely clear from corrosion after 700 hours salt spray testing or the cyclic corrosion testing. And this is a component that was passivated with our iridite products, and it has passed all the specifications. I want to move on to a different application, a different field of application here, and that is the aluminum anodizing. Again, becoming very important for the car industry to reduce weight or to further reduce weight on cars. Just a quick introduction to anodizing and what anodizing really is. I think everyone knows that aluminum can passivate itself in the normal atmosphere with a very thin oxide layer, and through that it can protect itself from any further corrosion. What we do in anodizing is, through an electrochemical process, we can actually control and grow this oxide layer on aluminum, and through that we can improve and enhance the corrosion resistance just by creating a much thicker oxide layer, aluminum oxide layer on the aluminum substrate. And if we look at the picture of an SEM picture of the aluminum surface here, what we have to do is we have to crack the surface, since we are not able to polish the cross sections. And what we can see here really on the left if we look down the side of this cracked edge, we see all these channels that run from the surface all the way down to the substrate of the aluminum. And these are the channels where the electrical current is conducted into the component, and it will actually further grow aluminum oxides from the base of the aluminum substrate. If we look on the right here, we see the pores on the surface. So we're looking directly onto the surface here, and we see these thousands and millions of little pores on the surface. These pores are tiny. They're ranging from 5 nanometers up to a size of maybe 20 nanometers. Let's go into some applications for anodizing, and I've picked two here, and the first one is aluminum brakes. Over the last few years and decades, it's become more and more popular to use aluminum brake systems, and again, this is done for reducing the weight on components. There are different systems available at the moment, and most of the systems we see is a combination of cast iron brackets and then aluminum caliper housings. One of the reasons that we haven't seen more aluminum housings and complete calipers in the automotive industry is really the wheel space available for these brakes. By nature, the aluminum has less strength and therefore needs to be dimensioned larger than a cast iron caliper, and therefore wheel space is limited for most vehicles, especially in the mid-range, and those wheels will not be able to accommodate a larger fully aluminum brake component. So that's mainly the reasons why these aluminum or aluminum cast iron combinations are limited to the rear axle of vehicles, where the forces or the brake forces are a little less, and these brake parts can be designed slightly smaller. The specifications that apply to these brake components are mainly tier 1 specifications and some OEM specifications. We can see that here there's the German specifications for brake calipers, the VDA. We have the tier 1s, Continental, TRW, and Brembo's, who have their own specifications and requirements when it comes to anodizing brake calipers. I've listed some of these requirements here, and I think that some of them are very self-explanatory. When it comes to appearance and color, everyone wants a very consistent, homogeneous surface that is aesthetically attractive. We have oxide layer thicknesses anywhere from 15 to 25 microns. Some of the OEMs actually specifying a hard anodizing or semi-hard anodizing up to 30 microns. Dimension tolerances, because the oxide layer actually grows out of the surface and will increase the size of the component slightly. These tolerances and dimensional changes have to be considered in drawings and are really specific to the tier 1s and OEMs here. Roughness requirements. Some of these parts are moving parts, especially when we talk about the pistons or some of the master cylinders. So every tier 1 will have a requirement for certain roughnesses for their particular components. Corrosion resistance, that varies greatly depending on the tier 1, and we have seen anything from 120 hours to 480 hours, and then just lately these corrosion specifications have gone up to as much as 720 hours. In cases where these brake components are actually dyed, especially with organic dyes, we see a light fastness rating of up to 8, which is one of the highest light fastness rating available here. Sealing quality, this is usually done by a dye drop test, and again we see ratings down to 1 or 2 to have a pass for these components. One of the problems and the great issues we have with aluminum for cast components is the silicon content in the component. It greatly depends on how the casting is manufactured, how the casting is actually cooled down, and how the silicon actually precipitates within the casting. And when we see the difference here between an aluminum sheet with a 1% silicon content and 8% for casting, we see great differences in the ability to anodize these surfaces and to also dye these surfaces afterwards. Especially here on the right hand side around the bleed hole, we see a very high silicon rich area, and this will almost give 0 points where we don't achieve an anodizing thickness at all, and therefore we're not able to absorb any dye particles and color the surface. When we look at a traditional and standard cycle for brake components, we tend to operate with a mild alkaline cleaners here, our oxidized C14, followed by a flash edge. We don't want to remove too much aluminum from the surface and liberate those alloying components. Again, then followed by a desmut to take away some of the alloying components on the surface. In some cases, we actually go through an electrobrightening process, especially for the lower silicon containing components where we have higher aesthetical aspects. We want to have a nice bright surface. Again, followed by another desmut, and then we anodize depending on the requirement here. It can be a standard type 2, and in some cases we hard anodize these components. We apply the final finishes here, the oxidized organic dyes, if required, and if not required, we'll go straight through the sealing processes to close all the pores and really give the component its final performance in terms of corrosion resistance, light fastness, so on and so forth. If this all goes well, then the final component, a final dyed component here, will look very attractive. It has a nice gloss to it, and it has a deep color and a very homogeneous surface and appearance as well. One of the other applications I want to talk about is the exterior trim and roof rails. And what we have seen over the last few years is that the specifications and the requirements for these exterior trims have been increasing significantly. And one of the reasons for that is that the medias we use in car washes becoming more and more aggressive, and that obviously has a significant impact on the anodized surfaces used on the exterior of a car. When we look at the requirements for these exterior parts, again, these are very visual parts. They have to be aesthetically very, very pleasing. So there's a very high requirement on a stain-free, no discoloration, no deteriorated component. The oxide layers depend a little bit on the final finish, whether we have a dyed surface, in which cases we use a slightly higher thickness. If we have a highly polished surface, we usually reduce the thickness to make sure that we maintain that luster of the aluminum surface. Corrosion resistance here for neutral salt spray, anything between 248 hours and 408 hours. And the cast resistance has gone up as well, anything between 8 and we've seen 12 hours as well. Humidity up to 240 hours. But the main requirement and one of the requirements that has consistently and significantly been increased over the years is the pH resistance. So where we started with pH 12, it has gone up over the years to pH 13 and 13.5. And this is really where the industry is working on at the moment, to have processes, chemical processes that can meet these high requirements. So if we look at a traditional process cycle here, we have the anodized surface, 5 to 12 microns, followed by the rinsing. Obviously, the coloring is optional depending on the final finish, and then after this anodizing and coloring, we have various options here of sealing the parts. Here on the left, when we look at alkaline resistance or pH resistance of less than 13.5, so this is your 12, 12.5 and 13, we normally find a sealing sequence that consists of a cold seal, followed by a hot seal or a nickel acetate sealant, again followed by an aging process, which is normally hot water with a small amount of desmutting agent, and then through rinses and the drying process. To meet the pH 13.5 and the highest requirement at the moment for the alkaline resistance, some people have, or some customers, applicators have changed and had no option other than changing to a electrophoretic lacquer. So the parts will actually not move through a traditional sealing process. The electrophoretic lacquer actually utilizes the porous structure of the aluminum substrate to key in the electrophoretic lacquer and offer very, very good adhesion properties here. And by nature, these electrophoretic lacquers are extremely corrosion resistant and will meet these high specifications. There are obviously downsides with using an electrophoretic lacquer. One of them would be to retrofit an electrophoretic lacquer onto an existing anodizing line. There's usually not a lot of space available, and additions of curing ovens, so on and so forth, and stripping lines to actually remove lacquer from components is not really a task that is easily accomplished. So what we are at MacDermid Enthone are working on at the moment is a different type of sealant stroke lacquer finish to meet this pH 13.5 requirement. And again, what we have chosen to do here is the traditional sealing sequence of the cold seal, the hot nickel, the hot seal, the nickel acetate seal, but this is then followed by an organic top coat, which can be applied as a dip lacquer. This is something we are very excited about, and it's in the making. And we're hoping to be able to launch this product or this sequence in the very, very near future. And this really brings me to very close to the end of my presentation. And just as a quick summary, the EV movement and the light vehicle movement has dramatically changed the demand for aluminum components. The corrosion requirements have increased. We have to deal with new applications like the battery casings that are exposed to certain environmental stresses and therefore need to be protected in different ways. So these battery enclosures have very, very different technical challenges in itself, and they need these OEM specifications to be rewritten and adapted and adjusted to them. As I said, the finishes, especially for exterior parts, have increased dramatically because of car wash medias, and to make these finishes last for a significantly longer periods of time. The challenges our industry faces is to really respond with technologies that make it cost effective to address and to meet these new requirements. And that is something we have been working on very, very heavily over the last few years. And we're trying to address that further and launch new products over the next few months to really make it easier for the applicator to deal with these new requirements and to meet these technical challenges. And that really concludes my presentation for today. I thank you very much for your patience. I know there's been a few hiccups at the start of the session. I hope that everyone managed to stick with it, and I hope that everyone enjoyed the presentation so far. I know that Rob will take over the back part of this presentation now. If there's any questions, I'm more than happy to answer these questions. If you would like to submit those questions directly to me, my email address and my mobile phone number are at the bottom of this slide here. And I encourage everyone to ask as many questions as possible.
So Sasha, we have one question that begs to be answered is, what is the benefit of rinsing after the hot water aging?
This is just, sometimes you have residues on the surface from the hot water rinse. Some people come straight out of the hot water rinse and use actually the energy of the hot water to dry the component. It's a preference. It's applicator's preference, really. No real reason.